Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about Eulerian multi-phase modelling approaches. So just to start with a quick overview of what I'm going to talk about today, I'm going to start by talking about what are dispersed continuous and continuous phase interactions and how are they different. I'm then going to look at what are the Eulerian multi-phase modelling equations, and I'm going to finish off by looking at what is interphase drag and how is it accounted for in the Eulerian multi-phase modelling approach. So just to start looking at dispersed and continuous phases, the Eulerian multi-phase modelling approach can account for both dispersed continuous phase interactions and continuous phase interactions. Now, don't worry if you're not too sure about what these types of phase interactions are, because I'm going to go through them briefly today, so you should have a good understanding of what they are and how they're different. Now, a dispersed phase can either be solid particles, liquid droplets, or gaseous bubbles. And these dispersed phases are typically very small, of the order of micrometers all the way up to millimeters in diameter. So the dispersed phases are typically very small and are dissolved in a continuous fluid, be that air or water or something of a much larger scale. And a dispersed continuous phase interaction would be the interaction between these small dissolved particles or droplets and the continuous phase. Now, in contrast to that, a continuous phase interaction occurs when two phases form a discrete interface between them, an interface that we can see. And this may occur with water and air, for example, or water and oil. And really, in a continuous phase interaction, we are interested in the location and the motion of that interface between the two phases. And for those interactions, the phases are typically immiscible in each other, meaning that they don't mix. So just to give you some real-world examples of these types of phase interactions, some examples of continuous dispersed phase interactions may be, for example, sprays and vapors. So when we have droplets which are dissolved in a gaseous or liquid spray, and we also find dispersed continuous phase interactions in humidity and air conditioning applications, where the dispersed phase are the droplets of water vapor which are dissolved in a continuous phase of air. And we also find dispersed continuous phase interactions in sediment transport applications, where we have small fine-grained solids, which could be sand or silts, dissolved in a liquid water phase, for example, and the sediment is transported along by that continuous phase. Now, these are all dispersed continuous phase interactions, but if we consider an application like free surface waves, or sloshing in a tank, or filling and emptying of a tank, those modelling applications are continuous phase interactions. And the reason for that is we are actually interested in the location and the motion of the interface between those two phases. So some of you, while flicking through your CFD user manuals or looking through research and on the internet, may have come across mixture models and volume of fluid models. Now, these models are simplified versions of the full Eulerian model that we're going to be considering in today's talk. And the full Eulerian model can account for dispersed continuous phase interactions and continuous phase interactions. Now, it turns out that the mixture model and the volume of fluid model are simplified versions of the full Eulerian model that we're going to be looking at today. And a mixture model is a simplified version of the full Eulerian model that's specific to dispersed continuous phase interactions, as we saw on the previous slide. Now, in contrast to that, the volume of fluid model is a simplified version of the full Eulerian model that's specific to continuous phase interactions. So you often see the volume of fluid model used in the literature for flows where you care about tracking an interface or a free surface. And really, just to summarize that slide, remember that both these models are simplified versions of the full Eulerian model that we're going to be looking at today. that can account for both types of interactions. So, what are the Eulerian model equations? Now, the thing that sets aside the Eulerian model equation from those other simplified models is that the Eulerian model solves a continuity or a mass conservation equation for each phase in our system. So if we have an air-water system, we'll be solving a continuity equation for the air, and we'll also be solving a continuity equation for the water. And this is different to mixture and volume of fluid models, where we only solve a single continuity equation for those cases. Now, the form of the continuity equation you see there in equation 1 is similar to the continuity equation that you may be used to for single phase flow, but with a few small differences. Now, the first difference is that all of the terms there on the left hand side are multiplied by the volume fraction of the phase Q that we're considering. And the reason for that is that we solve the full set of model equations for every cell in our CFD mesh, but physically the phase only exists where the volume fraction is greater than 0, and that's why we multiply by the volume fraction in each of those terms on the left. Now, we have an additional term on the right hand side of the equation, and this term represents the mass transfer between phases in our system. And typically the mass transfer term gets used for phase change processes like evaporation and condensation. So for an evaporation process, for example, we would be solving a two-phase system. We'd have liquid water and we'd have water vapor, and we'd be getting mass transfer between the liquid water and the water vapor. And for an evaporation, the mass transfer term there would be a sink for the liquid water, and it would be a source term for the water vapor. And just a quick note on the notation we're using here, the subscript PQ indicates mass transfer from P to Q, and that makes sense because the continuity equation there is written for phase Q, and so any mass transfer from phase P to phase Q is a source term in that continuity equation. And the other term, the m dot QP, represents mass transfer the other way, so that will be from Q to P, which will be a sink term, which is why it's negative there in the continuity equation. Now, how does the CFD solver distinguish between a dispersed continuous phase interaction and a continuous phase interaction? Because remember, for the full Eulerian model here, we solve the same set of transport equations for our domain, regardless of the type of phase interaction that we have. So what do we physically expect our solution to look like for these two phase interactions? Well, if we have a dispersed continuous phase interaction, the volume fraction should be able to take any value between 0 and 1. And what that would physically mean is that when we have a value of 0, we'd have none of our dispersed phase in those cells, and as the volume fraction slowly increases, that would indicate that the concentration of that dispersed phase in those cells is gradually increasing, and we can have any value there between 0 and 1. Now, if we contrast that to a continuous phase interaction, where we have a sharp interface between the phases, we expect on one side of the interface our volume fraction to be 0, where none of the phase is present, and on the other side of the interface a value of 1, where the phase is completely present. And so all of the gradients will typically be restricted to a few cells right at the interface. Now, we're solving the same set of equations here, but we've got two different types of phase interactions, and our CFD code needs to be able to distinguish between the two types of interactions. And in this talk today, I'm going to show you how we get the CFD code to distinguish between those interactions. Now, before we do that, the first thing we need to do is look at the volume fraction equation. Now, a volume fraction equation is going to be solved by our CFD solver for each additional phase in our multi-phase model. So that means if we have a two-phase system, say air and water, we'd only be solving one volume fraction equation. Whereas if we had a three-phase system, say air, water and oil, we'd be solving two volume fraction equations. And the reason we only need to solve n-1 equations is because we know in every cell the sum of the volume fractions has to equal 1. So what we can do is we can solve our additional volume fraction equations, add them up, and then subtract them from 1, and that will get us the volume fraction of the primary phase in those cells. And this approach of solving a separate volume fraction equation for each additional phase is common to the Eulerian model that we're considering today, the mixture model, and volume of fluid models. So how does the CFD code distinguish between dispersed continuous phase interactions and continuous phase interactions? Well, the way it does it is by using a special discretization scheme on the convection term, which you can see there highlighted in red. And normally for convection terms we'd use some form of upwind differencing scheme, and for those of you who've seen my previous video on convection differencing schemes, you'll have seen how we treat the convection term normally. And that's the same treatment that we would use here if we had a dispersed continuous phase interaction, because the volume fraction is free to take any value between 0 and 1 in our mesh. Now, if we want to artificially create a sharp interface between our two phases, then we have to use a special discretization scheme. And usually the choice of discretization scheme is left up to the user. And in your CFD code, you should have a variety of choices of schemes that you can choose from. And some examples might be a compressive interface capturing scheme or a piecewise linear construction scheme. And by choosing this form of the discretization scheme between phases, what we'll be doing numerically is enforcing that sharp interface between the two phases. And this is often termed an interface capturing approach in the literature. And this approach, of course, is going to be common to volume of fluid and full Eulerian models if we want to have a discrete and sharp interface between our phases. But of course it's not used by the mixture model, because in a mixture model it's implicitly assumed that we have a dispersed continuous phase interaction. And I'm not going to go into full detail on the convection differencing schemes for these terms because they're quite detailed and would need a full video in their own right. But you can look them up in the various user manuals for your CFD code if you need to know more about them. So in addition, the Eulerian multi-phase model solves a momentum equation for each phase. So in the same way that we did for the continuity equation, if we had a two-phase system like water and air, we would solve two momentum equations. We'd solve one momentum equation for the air velocity and one momentum equation for the water velocity. Now, one thing you'll notice by looking at equation 5 there is that the pressure P on the right hand side doesn't have a subscript Q. And the reason for that is that the pressure field is shared between all the phases in our system. And the pressure field is one of the ways that we couple the phases together in our solution field. And the other way that we couple the momentum equations together is by the source term on the right hand side there, which is highlighted in red. And this source term represents the momentum transfer between phases, so between the water and the air, for example. And if we start with those last two terms on the right hand side, we can see that we've got the mass transfer term in there, m dot. And if we think about it, if we've got a transfer of mass from phase P to phase Q, and that mass transfer occurs at a velocity u, then we're also going to be getting momentum transferred by that mass transfer. And that's why those final two terms are in there on the right hand side. They're really there for consistency. And in addition to that, we may get additional momentum transfer between the phases by additional forces such as lift and drag and virtual mass between the phases. And in today's talk, I've collected those terms together in a vector dpq. And as before, the subscript notation refers to P transferring momentum to phase Q, which is why it's positive, and it's a source term in the momentum equation for phase Q there. And we're going to dive in a little bit more detail to look at that interphase force between the two phases here. But before we do that, it's worth really thinking about the solution field and what our CFD code is actually doing. Now, if we consider a cell there, which you can see on the screen, for a two-phase system, it's important to remember that at the cell centroid, we're going to get a velocity field for each phase. So if we had a water and an air system, we'd have a velocity at the cell centroid, the water velocity, and we would also have an air velocity at the cell centroid. And these two velocities in the Eulerian model are different. And the reason they're different is due to those interphase transfer forces and the interphase drag that we saw in the previous slide. And it turns out that the predominant momentum transfer mechanism tends to be interphase drag, and it's the interphase drag that I'm going to focus on in today's talk. So for that cell we saw on the previous slide, what we're going to do is think that we've got a primary phase moving at a velocity u sub q, and then we've got another secondary phase moving at a velocity up. Now, these phases are not moving at the same speed in an Eulerian model, and there's a drag force acting between those phases. And if you remember, the general form of a drag force is going to be a half rho u squared times some contact area times a drag coefficient. Then the drag force can be written in the form given by equation 6 there. And this is common to all CFD models. This is termed the interphase drag force between phase P and phase Q. And of course, because this is a CFD code, our force has to be written per unit volume, because later the sources and the equations are going to be multiplied by the cell volume. And so the drag force per unit volume acting on that cell between the phases is given there in equation 7. And if we just take a minute to think about that equation, in our CFD cell, we know the velocities at the cell centroid, up and uq. There are unknowns in our momentum equation. We also know the density, rho q, but at this stage for our model, we don't know the drag coefficient CD, and we also don't know the interfacial area, it's AP, that's the contact area between our two phases per unit volume. So in today's talk, I'm really going to focus on the drag coefficient and the interfacial area per unit volume, because it's these two terms that are left up to the user to choose, and they're going to govern the drag force that you get between the two phases in your CFD model. So starting with the drag coefficient, assuming we have a dispersed continuous phase interaction, what we do is we assume that the dispersed phase, because it's very small, we assume that our dispersed phase is formed of small spheres. And if we have small spheres, then we know what the drag force is on a sphere moving through a viscous fluid. There are several models to capture this drag coefficient variation empirically. And if you remember back to your fluid mechanics textbooks or lecture slides or on the internet, you may remember a plot like that given below, where the drag coefficient initially starts high and starts to decrease with increasing Reynolds number. Now, the Reynolds number here for our particles is going to be the difference in velocity between that primary phase Q and the secondary phase P. So that will give us our particle Reynolds number for our spheres moving through our cell, and then the drag coefficient there. You'll often in your CFD code have the choice of many different drag models, but the most popular and the simplest is the Schiller-Neumann drag model, and that's the one I'm going to talk about today, given there in equation 8. And if for some reason you want to choose another drag model, that's of course up to you. Just make sure it's appropriate for your application. So we know the drag coefficient. What about the interfacial area or the contact area between the two phases? Now we know that in our model we've got a number of spheres in our cell, but we don't perhaps know the volume of the cell V at this stage. So what we're going to do in equation 10 is split up that fraction of the interfacial area per unit cell volume into two fractions. The first one being the volume of all those spheres in the cell divided by the volume of the cell multiplied by the surface area of all of those spheres divided by the volume of the spheres. And of course, if you look at equation 10, the volume of spheres cancels there if you want to get back to the original expression. Now, the reason we write it this way is that first fraction is of course the volume fraction of the spheres in the cell, Rp, and if we look at the fraction on the right hand side, well, the surface area of all the spheres divided by the volume of all the spheres. Doesn't matter how many spheres we have, that simplifies to the surface area of one sphere divided by the volume of one sphere. And we know what that is. That's going to be pi d squared for the surface area of a sphere divided by pi d cubed over 6. And then if we simplify equation 11, we reach this expression in equation 12 which is the interfacial area per unit volume, or sometimes called the interfacial area density for a dispersed continuous phase interaction. And you may see that written down in your CFD manual, and this is where it comes from. Now, of course, if we have a dispersed phase where our spheres have multiple different sizes, then what the CFD code will often do is give you the option of solving a transport equation to get the interfacial area per unit volume for the spheres. But I'm not going to cover that in more detail here. So what happens if we have a continuous phase interaction? Because clearly this is not going to be appropriate for that. Well, in that case, we're just going to use an identity, which is commonly used by all CFD codes, and that is if we've got two continuous phases in our cell, then the interfacial area, or the area that that drag force acts on per unit cell volume, is given by the magnitude of the gradient of the volume fraction. And the reason it's a magnitude is, of course, the gradient of the volume fraction will give you a vector, and then the magnitude of that will give you a scalar value, which we need for the interfacial area per unit volume. And this little picture there just gives you a little reminder of what's actually happening in our cell. If we have our two phases, our primary phase and our secondary phase, moving at velocities UP and UQ, then the drag force acts in the same direction as it does the difference in velocities. So in this case, the drag force will act to decelerate phase Q, and equal and opposite, it will act to accelerate phase P. And so that's the key momentum transfer mechanism in Eulerian model equations. So just a quick summary of what we've talked about today. The Eulerian multi-phase model, what differentiates it from a mixture or volume of fluid model is that we solve an individual mass, momentum and energy equation for each phase in the system. So if we have a two-phase system, water and air, we'd solve two mass conservation equations, two momentum, two energy equations for those phases. And for this reason, the Eulerian multi-phase model is quite expensive because we have to solve a lot of transport equations. And that's often the reason for choosing a mixture or volume of fluid model instead. Now, we can handle both dispersed continuous phase interactions and continuous phase interactions. And if we want a continuous phase interaction, the way that we enable that in an Eulerian or volume of fluid model is by introducing a sharp interface between the phases by selecting a special discretization scheme for the convection term in the volume fraction equation. Now, regardless of our phase interaction, we've seen here that it is the interphase momentum and heat transfer that really dictates how those phases interact and behave relative to each other. And it's the interphase drag that's the predominant momentum transfer mechanism and is the one you should choose most carefully when you're setting up your simulation. And of course, required for the interphase drag and the interphase heat transfer is the interfacial area per unit volume, which is sometimes called the interfacial area density, and it's going to be different if we have a dispersed continuous phase interaction or a continuous phase interaction. So I hope you've all found this talk useful. As usual, there's the useful references for you to look at are going to be section 16.5.3 for the ANSYS Fluent user guide and section 5.5.2 for the ANSYS CFX theory guide. If you want to have a look through both of those, they're both up on the internet if you want to do a bit more reading. And at this point, I'd like to thank you all for following my videos and continuing to support the channel. I really do appreciate it, and I really do enjoy hearing from you in the comments section below. So if you have any comments for this video or any of the others, feel free to leave them below and I'll get to them as soon as I can. And also just a reminder for all of you that if you'd like any further information, head on over to my website, and on my website you can pick up copies of the lecture notes that I've used here for all the videos on YouTube, and you can also find additional notes for some of my most popular videos and a range of useful and free calculators that you can use for common engineering tasks like choosing your cell height and selecting a settling velocity for your particles in your particle model. So I'd really recommend you head on over there and check out those calculators. I really think you'll find them useful. And at this point, just like to thank you all again for watching, and I'll see you in the next video.